Hello again, everyone. Today, we're going to move on to the next topic in the redox unit, which is the electrochemical cells. There's two words in it, electro and chemical. So we're dealing with electricity and chemical reactions, and you'll see how the two are tied in together. Uh, this unit is very cumulative. So everything we learned before has led up to this. So if you've been doing well in everything that we've done so far, then you should be able to take the next step. But these diagrams get a little bit complicated, and the Regents likes to show you these diagrams. So you really want to make sure you understand every step along the way in these processes that we're going to go through. So what are electrochemical cells? So these are devices that use redox reactions to either produce or use electricity. So we're dealing with a conversion between electrical and chemical energies, right? Remember our types of energies, that acronym CEMENT. So we have electrical energy, chemical energy are in that acronym as our types of our energies. So the anode, that's the electrode where oxidation occurs. And the cathode is the electrode where reduction occurs. So what are electrodes? So it says this up top. So separate surfaces called electrodes. These are solid objects, these electrodes, and they're usually metals. So these are solid pieces of metals, generally, right? So there's two types of electrochemical cells. We have the voltaic and the electrolytic cells. So think about electricity. We measure electricity in voltage. So voltaic cells, the easy way to remember that is think voltage. They produce electricity. Voltaic cells produce electricity via a spontaneous redox reaction. So remember, these spontaneous reactions are reactions that occur all by themselves. When you put the substances on contact, they react. So what do we have going on here? B is really the easy way to remember this, right? And if I ask you, describe how a voltaic cell works or what it does, it converts chemical energy to electrical. So we're taking the chemical energy from our reaction and converting that to electrical energy. And we'll see how that works as we go through the process. Now, electrolytic cells are a second type of cells, which we're going to get to in the next lesson. This lesson, we're going to focus on voltaic cells. So electrolytic cells are basically the opposite of a voltaic cell. They use electricity to drive a non-spontaneous redox reaction. And how they work, again, this is the easy way to explain it. They convert electrical energy to chemical, right? So if I ask you to explain how voltaic and electrolytic cells work, these are the easy ways to do that. Voltaics convert chemical to electrical, electrolytic convert electrical to chemical. It's essentially the opposite, okay? So today we're going to focus on voltaic cells. So these are the diagrams that you tend to see. So you're going to want to know all the different parts of this and how these work. So they'll ask you to label things, answer questions about it. So I'm going to show you the basics. And these get a little bit complicated, but if you remember the basics, you'll be able to answer the majority of the questions that you'll see about these cell setups. So voltaic cells are composed of two half cells of different metals used to produce an electric current. And what is an electric current? It's a flow of electrons. So electricity, remember, is a flow of electrons. That's what electricity is. So how does that flow of electrons occur? So let's talk about that. So here's your setup here. So we have two pieces of metal. These are our electrodes. So here's our zinc electrode, solid piece of metal. And here's our copper electrode, solid piece of metal. If we were in class, I would show you actual examples of these. So, and then we'll talk about this upside down U-shaped thing in a minute. And remember, these are always in solutions of their own ions. So this is a 1 molar solution of zinc ions, and this is a 1 molar solution of copper ions. All right. So, and now let's think about our oxidation states too. Since these are uncombined metals, they're in their elemental state, they're uncombined, they're always going to have oxidation states of 0. So why don't you go ahead and put those in, right? And then we're going to draw our ions in solution. So the zinc metal is in a solution of zinc ions, and the copper metal is in a solution of copper ions. These are in separate containers, so these are our half cells. Because remember, we're dealing with an oxidation reduction reaction. So in one cell, half of the process is going to occur, the oxidation half, and in the other cell, the other half is going to occur, the reduction half. So that's why they're called half cells, because half of the oxidation reduction process takes place. All right. So let's just walk through this diagram. So what is this upside down U thing? This is called the salt bridge. So the salt bridge is a tube containing a conductive solution. That's our salt, right? That's our salt. Remember what a salt is, your ionic substance. So that allows the movement or the migration, they like to say that word, migration of ions, but prevents solutions from mixing. So the Regents likes to say this kind of phrase right here, migration of ions. So if you're asked what is the function of the salt bridge, migration of ions. That's the easy explanation. Those 3 words, remember that, you'll always get the question right. There's other ways you can explain that, but easy way is migration of ions. All right. Let me move my face out of the way here. All right. So that's the salt bridge, and that's this thing right here. It's a bridge connecting the 2 half cells. So why do we need that bridge? You'll see as we go through, right? So next thing. So remember the basics. I'm going to show you like 4 things here that you want to remember. And if you remember those 4 things, you'll get the majority of these questions right. Even though they might be a little bit complicated, try and remember these things and label the certain parts of the diagrams, and that should be able to lead you in the right direction. So one thing we want to remember, electrons always flow away from the anode, AA. So the anode gets oxidized away from the anode. AA, electrons always flow away from the anode. And then the other thing you want to remember is the metal that is higher on table J is oxidized. And we talked about that the other day too. The higher metal on table J is oxidized. All right. So, and again, remember what it means to be oxidized, right? That's a loss of electrons, right? Leo, that's coming up too. So again, think a lot of times with electricity, we'll use water as an analogy. So when you're talking about the higher metal is oxidized, oxidized means you're losing electrons. So think like water flows down. So the higher metal on table J, so let's take a look at table J again. So the higher metal on table J loses electrons to the lower metal, whoever that lower metal might be. So think like water flows down, right? The higher metal is going to lose electrons to the lower metal. So that's oxidation. Loss is oxidation, right? So maybe that helps. These little tricks all help. So the other thing you want to remember, anox and red cat. So we just mentioned that before. The anode is always the site of oxidation, and the cathode is always the site of reduction. So just remember our animals here, our friends. So we have our lions, our oxen, our cats. So a lot of animals are helping us out here. And then don't forget, Leo says grr. So these 4 things are really going to help you out. So put a little bracket there, star that. Remember these 4 things, and you'll be able to answer the majority of these questions, like I said. So anode is always the site of oxidation. Just think anox, like, hey, look, there's an ox. Red cat, and then good old Leo says grr, to remember that your loss of electrons is oxidation and your gain of electrons is reduction. All right? So when you get these diagrams, you're going to want to go through and label this stuff here, because that's going to help you answer these questions. So the first thing you want to do is kind of label who's your anode and who's your cathode. All right. So the easiest way to do that is once you see a salt bridge, go right to table J. Go to table J and look for the higher metal, because that's going to tell you the higher metal is the anode, right? Oxidized. So the metal that is higher on table J is oxidized, loss of electrons. So that's again the anode. That's what we're looking for. So that's the first thing. So the second you see it's a voltaic cell, how do you identify it? You see that salt bridge there, right? The electrolytic cells look a little bit different. We'll get to that in the next lesson. So go to table J. So the second you see one of these diagrams, go to table J. So now we look on table J and we say, okay, who's higher, zinc or copper? Well, here's zinc and here's copper. So zinc is higher, right? So that's all you got to see. Who's higher? So zinc is higher. So what does that tell us? Zinc is the anode, right? The higher metal is the anode. Zinc is the anode. So what do I know about the anode? It's oxidized. That's where oxidation is occurring, right? The anode is where oxidation occurs, right? So that, what does that make the copper electrode? That makes it the cathode. So process of elimination, right? There's two electrodes. If one's the anode, the other is the cathode, which is the site of reduction, right? The cathode is the site of reduction. So now the next thing you want to be able to do is look at our four things to remember here. Electrons flow away from the anode. So if I know who my anode is, which I labeled, I know which way my electrons are flowing, away from the anode. So let's draw that in there, right? Right there. Electrons are going this way. So if you're asked which way the electrons are flowing, do not say away from the anode, right? Be more specific about in relation to the electrodes in the diagram. You could say to the right, you can say away from the zinc towards the copper, whatever, right? But don't say away from the anode, because if you don't have the anode labeled, then I'm not going to know which direction you're talking about, and I can't assume that you know who the anode is. All right, so be specific. All right, give a direction that's easy to understand without any further information. All right. So electrons flow away from the anode. All right. So now that you know this, you can answer the majority of your questions that are going to come up. All right. But now, why do the electrons flow away from the anode? Because zinc is oxidized. It's losing electrons. So zinc is losing electrons, and because we're in two separate containers here, right? One half cell, the other half cell, I can't have a direct transfer of electrons from zinc to copper, right? The only path I can go through is through the wire. So by having this particular setup here and connecting these electrodes by a wire, it forces the electrons to go through this wire, right? So that flow of electrons is what we can then get to do work, right? This is where you would have plugging in your device or whatever. If you had a little light bulb here, right, you would plug your light bulb in. Right, there's my little light bulb, and it would light up as the electrons are passing through doing work. So this is essentially a battery, right? That's what a voltaic cell is. It is a battery. So it is chemical energy inside of that battery that is being converted to electrical energy, and that electricity is powering your device, whatever you hook that battery into. When those zinc atoms lose electrons, they then become zinc ions. In this case, zinc is going to lose 2 electrons, sends those electrons up through the wire, and then those zinc ions go into solution. So when the zinc atoms become ions, they now go into solution, right? Those electrons get sent up over down here, and they build up on the cathode. All right, those electrons then come over here and build up on the cathode. Now you have all these negatives building up on this cathode here. All right, so what do these copper ions do? They go, hey, look at all those electrons. I want some of those electrons because I'm positively charged. So I'm attracted to those negatives. I'm going to go over and pick up those electrons. So what is a gain of electrons? Reduction. So this is where the reduction takes place. So the copper ions come over, pick up those electrons, and become copper zero. But what's copper zero? A solid. So when it picks up those electrons, it then comes out of solution and deposits itself on the cathode, right? So those copper ions come out of solution and deposit themselves on the cathode when they get reduced, okay? So this is a complicated process here that you want to try and understand as best as you possibly can. All right, and the other thing we want to remember here is the anode over time, as these zinc ions are going into solution, right, we're losing zinc zero, so it's going to get smaller. So over time, my anode is going to get smaller. So as we keep oxidizing, this is going to get smaller and smaller and smaller and smaller, right? Because the zinc zero is oxidized and it goes into solution. So as we're oxidizing these zinc zero atoms and they're going into solution, this is going to get smaller and smaller and smaller. What happens over here? Well, as we're reducing copper ions and they deposit themselves on the cathode, this is going to get bigger. So sometimes it helps to just not remember red cat. Think fat red cat, because the cathode gets bigger and the anode gets smaller, right? So if you think of this, like I said, it's a battery. Batteries don't last forever. So eventually we run out of either oxidizable or reducible substance, and then your battery is dead and you have to replace it. So these things don't last forever, right? So now again, back to maintaining neutrality. As these zinc ions are going into solution, we're getting more and more and more positive. So we want to try and maintain neutrality so that these electrons can continue to flow from one side to the other. So what do? We need some negative ions to cancel out all these positives. So that's the job of the salt bridge. The negative ions will move into the anode side to help cancel out that surplus of positive ions as the zinc zero is getting oxidized. And then what's happening over here? Well, as we're losing positive ions and they're getting reduced, the positive ions from the salt bridge, in this case potassium, are going to flow into the cathode side in order to replenish that positive ion supply in order to keep things neutral, right? Because even though we're losing positives, there are still negative ions in solution in here, whatever they might be. So as we lose positives, the negative charge is building. So we need to bring positives into there to keep things neutral, right? Once we get a charge development on either side, like think about this side. If we just had an increase in positive ions, as this side becomes more positive, what alike charges do? Repel, and opposites attract. So if I build up a positive charge here, that positive charge is going to attract those negative electrons, and that flow of electrons is going to stop, right? And the same thing over here. If I have a buildup of negatives, if my negative charge builds up over here, that's going to repel the negative electrons and push them back towards the anode and stop the flow of electrons. So the salt bridge is very important in this process here. Without the salt bridge, you don't get a flow of electrons. So remember, any circuit is going to conduct electricity only when the circuit is closed, right? So this is a closed circuit right now, right? We got this flow of electricity that's going through here, all right? We take this salt bridge out, that's like turning a light switch off. It opens the circuit and the flow of electricity stops, all right? So this is a complicated process here. So you really want to try and understand it as best as you can, right? So again, what's taking place here? The anode is oxidized, right? So how do I know who the anode is? Higher on table J. Whoever's higher on table J is the anode, right? So once I know that, then I know my direction of electron flow. Electrons always flow away from the anode. I know who my cathode is, which is always the site of reduction. So now I know who's oxidized, who's reduced, who's the anode, who's the cathode, and which way electrons are flowing. And all that came from just looking at table J first, right? So now again, what's the process? Why are electrons flowing in this direction? Because zinc atoms are losing electrons and becoming zinc plus 2 ions. They're sending those electrons up, over, down onto the cathode, and they're building up over here. Then those copper ions in solution, they're going to come over here and pick up those electrons and get reduced. When they do that, they deposit themselves on the cathode. All right. So over time, the cathode is going to get bigger and the anode is going to get smaller. That's it. So when does the whole process stop? When we either open the circuit, right, take out the salt bridge, pull out one of these electrodes, or if we run out of substance, right? If we run out of oxidizable, reducible substance, the process will stop, right? So that's a voltaic cell, and that's how it works. Try and keep it simple. It can get complicated very quickly, so just remember the basics, and you'll be okay. And the last thing are the charges of the anode and the cathode. So when you look at a battery, there's a positive end and the negative end. So the negative end is the anode, right? That's where the electrons are coming out of. And the positive end is the cathode. That's where the electrons are going into, okay? So they're not actual charges. They're just ways of kind of keeping track of the direction of electron flow. So the electrons always come out of the negative. That's why they label that negative. And they go into the positive because opposites attract. So they're not really the charges here, because remember, we're trying to keep things neutral. They're just giving us an idea of which way the electrons are flowing. So the electrons go from the negative to the positive, right? So this is where electrons are being produced. So that's why we call the anode negative. And they're going to the cathode. So the cathode is positive, right? So that's pretty much it. So now we want to figure out who is oxidized and reduced and be able to write the half reaction. So as I've said before, this unit is very cumulative. So everything we've done before is coming into play here. And it's all kind of up here. You just got to pull out the relevant pieces. So who's oxidized? Zinc 0. So zinc 0 is oxidized. So zinc 0 is becoming zinc plus 2 by losing 2 electrons. Now, who is reduced? So we know copper is getting reduced because reduction is taking place over here. But which copper? So think about what reduction is. It's a gain of electrons. Who is gaining the electrons? The ion. So copper plus 2 is the one that's gaining electrons. So now let's construct our half reaction. So zinc 0 is becoming zinc plus 2 by losing 2 electrons. Done, right? Remember, losing, electrons are leaving, they're on the right side, they're exiting the equation. And then copper plus 2 is gaining 2 electrons to become copper 0, all right? So don't make the common mistake of saying that copper 0 is reduced. The cathode is where reduction occurs. It doesn't necessarily mean that it's being reduced. The ion gets reduced, all right? So generally here, the ion gets reduced. So keep that in mind, and that'll help you out. The ion gets reduced. Because remember what reduction is. We're gaining electrons and becoming copper 0. And that's it. So if you can get to the point where you can tell me who's the anode, who's the cathode, who's oxidized, who's reduced, which way electrons are flowing, and construct the half reactions, that's really the majority of what you'll ever need to be able to do, right? And if you get anything about the salt bridge, what's the function of the salt bridge? 3 words: migration of ions. That's the easy way to explain that. Let's give this a whirl. So take a look at this activity sheet that's attached to the lesson. You can skip numbers 2 and 10. So pause the video, try and go through and answer these questions. Right, you might want to label the anode and the cathode, who's oxidized, who's reduced, right in the direction of electron flow in the diagram, and then use that information to answer the questions. All right, so take a second, use table J, try this out, and then unpause it, and we'll go over the worksheet. All right, so let's go over this. So first thing we want to do, go to table J. So when you look on table J, you're comparing aluminum and lead. Who is higher? So aluminum is higher on table J. So that makes aluminum the anode, which means it's oxidized, anox. And then that means lead must be the cathode, which is where reduction occurs. So oxidation occurs at the anode, reduction occurs at the cathode. So now, just by that, we know the direction of electron flow away from the anode. So write that in. Electrons are flowing to the right. So now let's answer our questions here. Which is the more easily oxidized metal, aluminum or lead? So aluminum. Why? Because it's higher on table J. Number 4, what is the direction of electron flow? We said that already. To the right. Figured that out. So you're just using what we figured out to answer these questions. What's the direction of positive ion flow in the salt bridge? So this is a little tricky. So you see something like this, which isn't too often. This is a tough question. So remember what's going on here. Let's go back up to our diagram. So we have aluminum ions in solution, and then we have lead ions in solution over here. So as our aluminum is oxidized, it loses electrons, sends them up over, and they build up over here on the cathode, right? Those negative electrons build up over here. And then as the aluminum is oxidized, aluminum ions go into solution. And then as the lead ions are reduced, right, they're going to come out of solution and deposit themselves on the cathode. And the cathode's going to get bigger over time, right? This is going to get bigger over time. And then remember, we want to maintain neutrality in these half cells. So that's where the salt bridge comes into play. So what's the purpose of the salt bridge? Well, let's say I have a negative ion up here, whatever it may be. And then I have a positive ion in here too, whatever it may be. So because I have an increase in positive ions as the aluminum 0 is oxidized, whatever those negative ions in the salt bridge are, they're going to come into this side and to try and keep things neutral. So more positives, we bring in more negatives, maintain neutrality. Over here, as I'm losing positive ions that are getting reduced, I'm going to bring in more positive ions from the salt bridge to, again, maintain neutrality. As I maintain neutrality, I can continue to have a flow of electrons. So what's the direction of positive ion flow in the salt bridge? To the right. The positive ions are going to go into the lead side, the cathode side. Number 6, which electrode is going to decrease in size? Well, fat red cat, cathode gets bigger, so the anode gets smaller. So aluminum is going to get smaller. Over time, this is going to get smaller and smaller and smaller and smaller as more and more of those atoms are oxidized. And then which electrode gets bigger? The cathode, the lead, right? Because we're gaining atoms as they're getting reduced and depositing themselves on the cathode. So what's happening to the concentration of aluminum ions? It's going up. Because as they're oxidized, they're going into solution and it's increasing. What's happening to the lead ions? They're decreasing because they're getting reduced and coming out of solution. Who is the anode? Aluminum. Who's the cathode? Lead. Which electrode is positive, right? So remember, use your direction of electron flow to help you out. And remember, opposites attract. So if the electrons are drawn towards the cathode, If electrons are negative, the cathode must be positive. And if the electrons are being pushed away from the anode, like charges repel, so the anode must be negative. So which is the positive electrode? Lead. What's the negative electrode? Aluminum. So that's it. If you got all these right, you're doing great. If not, go back, rewatch the lesson, really try and understand this well. Next lesson, we'll go over the electrolytic cells, and we'll also recap this and review. So really try and have a good understanding of these voltaic cells going into the next lesson. So I'll see you all next time.